So the another aspect that I was alluding to, which is often used in designing constant voltage supplies, is the following. Let me motivate the principle behind it, and we'll come back to the actual implementation of it at a later stage in this course. But the thought process is as follows. So what is the main reason behind burning excessive power while we were trying to drive a resistive load? The main reason was as follows. The load was connected here. So the main reason was, as this resistance was changing, it was changing the effective resistance of this box. As that RL was changing, this was changing the effective resistance looking down, right? The parallel combination of R and RL was changing the effective resistance with respect to the resistance that was attached on top of it, right? So as RL was changing, the division ratio, the resistive division ratio was also changing, correct? So that is why it was being difficult to maintain a constant voltage across. It was getting difficult to maintain a constant voltage across this terminal. So what did reducing R do? Reducing R sufficiently ensured that this division ratio becomes largely insensitive to RL, right? If the division ratio is largely insensitive to RL, then it's not a problem. Then I can always maintain approximately constant V0, right? So therein lies the problem, and therein also lies a potential solution. What is the potential solution? The potential solution is, what if instead of using a fixed R, what if I say I will do this? I know that this RL is variable, right? So let me call this one R1 and let me call this R2 for the time being. What if I also make R1 to be variable, right? How we will make R1 to be a variable is a story for another day. But what if we make R1 to be also a variable resistance? If we can make R1 to be variable resistance, then it is probably possible to ensure that this division ratio of R2 parallel RL and R1 become unity, or rather become half for all values of RL. In principle, this is possible. But how, if you have to do that, what do you need to do? Because note that this RL can change. If RL changes, I'll have to ensure that the information of the change of RL gets captured and then transferred to R1, right? So in principle, we need a block that can observe a change and feed that information into R1, right? So what is this block supposed to do? This block is supposed to observe change in RL and adjust R1 accordingly. Right? So in other words, I need to feed back the information from the output, that is from RL to R1. So that is why negative feedback becomes, our feedback networks become a very important aspect of analog circuit design in the context of controlling things, right? So as I had mentioned in the introductory video, this course will be as much about designing an amplifier as it will be about designing an amplifier from the perspective of negative feedback, right? So this is one of the motivations of why negative feedback is important. That is, in order to control an output voltage effectively or efficiently, we need to observe the change in output and feedback that information somewhere in the network to make an adjustment. Right? So because in principle this is what we would like to do, hence in principle negative feedback is something that we will be focusing on for a major part of this course. Okay, so we will come to a more formal way of introducing negative feedback few lectures down the line, but let me concentrate on one more extremely important aspect that we will be covering in this course, or we will be using in this course. It's extremely simple idea. We all know about it, but I would like to reintroduce it from the perspective of resistances and keeping and identifying which block can drive which load, or which block cannot drive which load, or another way of saying the same thing is under what condition a particular block that you are designing will be able to drive a certain load or might not be able to drive certain load, right? We have already seen that example. We have already seen the example from the perspective of a resistive divider, but let's try to see another example. Even though this is a very simple concept, right, we'll be using it time and again throughout this course, so it makes sense to go over it one last time. Okay, so let me try to convince you about this importance with a thought experiment. So let's assume that I went to a electrical store. I bought a battery. Okay, so let's say I went to an electrical store and I asked for a battery. So I got a box. I don't know what's inside the box. I have been told that this is a battery and this comes with two terminals. Okay, I am fairly certain that this is an LTI network inside, right? Let's say this is an LTI network inside, right? Okay, so what I do, I come home and I put a voltmeter between these two terminals. Let me mark these terminals as A and B, right? I put a voltmeter between these terminals and I observe, right? I observe VAB under this condition is equal to 1 volt, right? Then can I conclude from this observation that this is indeed a voltage source? I obviously cannot, right? Because what is the property of a voltage source? A property of a voltage source is that, so what is a voltage source? So voltage source, the major property of voltage source is the voltage across its terminals is insensitive to any load attached between its terminals. Correct? This we all agree, right? So how does the statement that I just made any different from the observation that we have made? The observation that we have made is for an open circuited load, right? We haven't really tested out whether the voltage source is, whether this stuff that I have bought from the market is actually a good voltage source or not, because I haven't put any resistances across its terminals. Okay, so what I did was, I said I couldn't find any resistance lying around. So what I did, I went ahead and shorted the terminals A and B, right? So what I did, I experiment 2, right? So this is experiment 1. I did this. So let's say I do an experiment 2. In experiment 2, I go ahead and do this. Again, same network. I know this is an LTI network. What I did, I go ahead and short these 2 terminals, and I observe this current, and I call this IAB, or let me just simply call it ISC. It's a short circuit current. We call it ISC. I observe that this is equal to 10 milliamps. Now, from this observation, can I conclude that this is a current source that supplies a current of 10 milliamps? Again, obviously I cannot conclude this from one experiment, because what is the definition of a current source? What do we understand by a current source? The current through the terminals is independent of the load attached. If it has to be a current source, then the current through the terminals has to be independent of the load attached to it. Now mind you, I haven't attached any load, I have just simply shorted the output. So from these 2 experiments, can I conclude that the stuff that I have bought from the market is it a good voltage source or is it a good current source? Actually, I cannot conclude either, because I have some missing information. And what is the information that is missing? Now we all know that if this were a good voltage source, right? If this were an ideal voltage source, then what would have happened if I had shorted the terminals A and B? If I had shorted the terminals A and B, I should have seen an infinite current, right? An ideal voltage source doesn't have any internal resistance, right? So let's assume this stuff inside my LTI box is an ideal voltage source. If this were an ideal voltage source and I did the experiment 2 by shorting these 2 terminals, this is A and B, what would this current have been? This ISC would have been infinity. However, what do I see? I see a limited current. The current is limited to 10 milliamps. So what can I conclude? I can conclude that this is not an ideal voltage source, and the fact that there is probably a resistance associated with the voltage source. So there is a resistance Rs associated with the voltage source, right? Correct? Since I have a resistance Rs associated with the voltage source, the short circuit current is instead of ISC, the short circuit current is 10 milliamps. So now what is 10 milliamps? This, I have a battery. What is 10 milliamps? 10 milliamps ISC is V bat by Rs, which is 10 milliamps. What is V bat? From where do I know V bat? This was experiment 2, right? This is experiment 2. What was experiment 1 telling us? Experiment 1 was telling us that if this contraption was open circuited and I was measuring this voltage VAB, correct? I was getting VAB to be equal to 1 volt. And what is VAB in terms of VBAT? Because the current that I am drawing is 0 because of open circuit, my VBAT, VAB is equal to VBAT, which is equal to 1 volt. Which means what? Which means my VBAT is 1 volt and my RS is 1 volt by 10 milliamp, which is 100 ohm. So essentially, the stuff that I have bought from the market is this, is 1 volt, 100 ohm, and this comes inside my box. Okay, I had gone to the market to get an ideal 1 volt, but when I came back with this contraption, right? So now, is this a good voltage source or is this a good current source? What can I infer from this? I will argue that I cannot infer anything from this information. Why? Because whether this is a good voltage source or a good current source depends upon what resistance am I planning to drive. Let me elaborate. So if I connect a resistance RL, what is the voltage VAB? VAB is 1 volt times RL by RL plus 100 ohms. Let me express this in terms of the internal resistance of the battery. Okay. So under what condition this VAB will not change regardless of the values of RL? Right? What is the definition of a voltage source? Let me take you back to the definition of a voltage source. The definition of a voltage source is that thing that is insensitive to any load that is attached between its terminals. Now there is a load RL attached at the terminal. However, my VAB should not change if this bar is supposed to be a voltage source. So for voltage source, for the box to behave like a voltage source, what should get satisfied? We should ensure that those ranges of RL for which RL is much greater than RS, right? For these ranges of RL, my contraption inside the box will behave like a voltage source, right? So if you satisfy this, if you use this box to drive those values of load resist, rather if you use this box to drive load resistances which are much greater than RS, which in this case is 100 ohms, then this will behave like a voltage source, right? Your output voltage will remain insensitive to the change in RL. Now, can this box behave like a current source? So what should I try to see? I should try to see what is the current, right? What is the current through this load, right? So what is the current? IRL. My current is 1 volt divided by RL plus RS, right? And what is the definition of a current source? The definition of a current source is that contraption whose output current is insensitive to the change in any load resistances, right? So under what condition this output current is independent of RL? This will be independent of RL under the condition that, so if RL is much less than RS, right, then IRL is 1 volt by RS, which is 10 milliamps, for all values of RL which is much less than 100 ohm. And hence, under these ranges of RL, right, under these ranges of RL, this box will behave like a current source, right? Note that the same box, I went to the market and asked for a voltage source, but the same box can behave like a voltage source or like a current source depending upon the range of load that you are trying to derive, right? So in other words, if I mark the range of RL, right? So if I say RL is much less than 100 ohm, this behaves like a current source, right? RL much greater than 100 ohm, my box behaves like this box behaves like a voltage source. But if it's in around the range of, if RL is of the order of 100 ohm, then this is neither a voltage source nor a current source, right? In that range, both the currents through RL and the voltage across RL are dependent on the load resistances. So now, if you are somebody who is in charge of designing the box, that will be our job in a different context. That is something that we will be doing throughout the course. We will be in charge of designing the parameters inside the box. What is the first question that you should ask? The first question that you should ask is that, okay, fine, you have asked me to design some block, maybe some amplifier or maybe some regulator, but what is the load that I am planning to drive? Because it is dependent on the performance of my block, will be dependent on what am I trying to drive. And what is this dependent on? It is dependent on the Thevenin resistance that I am seeing at the output of the block, right? If I know what is the Thevenin output resistance of the block that I have designed or the block that I am planning to design, then I can make a quick and dirty approximation to figure out whether this block will behave like a voltage source or will behave like a current source for the ranges of load resistance that have been provided to us, or it might not behave either like a voltage source or a current source. So this also becomes important when you are debugging a circuit, right? When you are debugging a circuit and you see that your output voltage is changing when it's not supposed to change, or your current is changing when it's not supposed to change, what is the first thing that you should go and check? One of the first things that you should go and check, whether the Thevenin equivalent resistance at the output of your block is either very high or very low, depending upon with respect to the load resistance that it is driving, and it depends on what you are trying to make, right? So what is the conclusion of whatever we have been focusing on for the last 2 lectures? Essentially, these last 2 lectures were a motivation behind all the things that we'll cover in this course, right? So what was the first motivation? The first motivation is we need a block for amplifying power. Second is we need to understand feedback design, power efficient solutions. And what is the third thing? We need to pay attention to the output resistance of a block that is driving certain loads, right? So these are the 3 bedrocks, right? These are the 3 bedrocks of this course, or rather you can say that these are the 3 targets that we plan to get comfortable with as the course progresses. The final one, this one is super important, right? We'll be using it day in and day out, right? So because we need to pay attention to an output resistance of a block, or for that matter some equivalent resistance of a block, or for that matter Thevenin resistance of a block, we need to brush up our basic circuit theory problems on figuring out resistances of a block. So what I will do is I will post an assignment in the first week, which will be a refresher of figuring out output resistances, or rather resistances of different types of linear time invariant circuits, right? You can go through them, and this first lecture this first assignment will be a refresher or a revision of the concepts that we already know, right, from our previous experiences of dealing with basic circuit theory, right? And we can then take it forward from there.